Deep beneath the earth, in an abandoned gold mine, a tank filled with 100,000 gallons of cleaning fluid waited in darkness. This wasn't a storage facility or a forgotten industrial relic. It was one of the most important scientific experiments of the 20th century, designed to catch the most elusive particles in the universe. Raymond Davis Jr. was a man on a mission to detect the invisible. Born in 1914, this American chemist and physicist would spend decades pursuing particles so ghostly that trillions of them pass through your body every second without you ever noticing. These particles are called neutrinos, and Davis dedicated his life to proving they exist. Neutrinos are among the strangest inhabitants of the subatomic world. They have almost no mass, carry no electric charge, and interact so weakly with matter that they can pass through entire planets as if nothing were there. They're born in the nuclear furnaces of stars, created when hydrogen atoms fuse together to form helium. The sun alone produces an incomprehensible number of them, flooding the Earth with billions upon billions every second. How do you detect something that ignores almost everything in its path? Davis had an answer, and it was brilliantly unconventional. In the late 1960s, Davis and his team descended 1,500 meters underground into the Homestake gold mine in South Dakota. They installed a massive tank filled with perchloroethylene, a common dry cleaning fluid. The choice wasn't random. This chemical contains chlorine atoms, and on extremely rare occasions, when a neutrino strikes a chlorine atom with just the right energy, it transforms into an atom of argon. The experiment was an exercise in patience and precision. Every few months, Davis and his colleagues would extract the tiny amount of argon produced in the tank. They were looking for individual atoms in a 100,000-gallon ocean of cleaning fluid. The technique required extraordinary sensitivity and meticulous care. Each argon atom was a messenger from the sun's core, proof that neutrinos were real. The Homestake experiment succeeded. Davis detected solar neutrinos, confirming their existence and opening a new window into the sun's interior. But the results contained a puzzle that would perplex physicists for 3 decades. The detector was catching only about 1/3 of the neutrinos that solar models predicted should be arriving from the sun. This discrepancy became known as the solar neutrino problem. Either our understanding of how the sun works was fundamentally wrong, or something strange was happening to the neutrinos on their journey from the sun's core to Earth. The scientific community was divided. Some questioned the solar models, others suspected the experimental technique, and a few proposed that neutrinos themselves might be more mysterious than anyone imagined. Davis remained confident in his measurements. Year after year, the Homestake detector continued its silent vigil, counting neutrinos and consistently finding fewer than expected. The experiment ran for over 25 years, accumulating data that would prove crucial to solving the mystery. The resolution came from understanding that neutrinos aren't just one thing. They come in 3 types or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. The sun produces electron neutrinos, and Davis's detector was specifically designed to catch them. But as neutrinos travel through space, they can oscillate between flavors, transforming from one type to another. This phenomenon, called neutrino oscillation, meant that by the time solar neutrinos reached Earth, many had changed into muon or tau neutrinos that Davis's detector couldn't see. The sun was producing exactly the right number of neutrinos. They were simply changing their identity during the journey. This discovery had profound implications, proving that neutrinos must have mass, however tiny, which contradicted earlier assumptions in particle physics. Raymond Davis Jr.'s persistence and ingenuity fundamentally changed our understanding of both the sun and the nature of matter itself. His work demonstrated that the most challenging experiments can yield the most profound insights. In 2002, at the age of 87, Davis received the Nobel Prize in Physics for his pioneering contributions to astrophysics, particularly for the detection of cosmic neutrinos. In 2002, at the age of 87, Davis received the Nobel Prize in Physics for his pioneering contributions to astrophysics, particularly for the detection of cosmic neutrinos. Davis showed us that the universe is stranger and more wonderful than we imagined, and that sometimes the most important discoveries come from looking where others thought nothing could be found.